In this lecture, I want to continue the discussion that we started in class on how to convert a circuit from the time domain to the frequency domain. So what I have here is a table from your textbook. It's table 13.1. It should be in all editions of the textbook. That basically illustrates the time domain relationships on the left-hand side of the table and the frequency domain relationships on the right-hand side of the table. So you can see here, for example, for the inductor, we have the equation V is L di dt. The voltage is shown as a positive drop from A to B, and the current is shown in the passive sign convention direction from plus to minus. So the first thing I need to point out is if you're solving a circuit and for whatever reason the directions of the current and voltage do not agree with this figure, then you'll have to have a negative sign somewhere in your equation. So the equations and the sign on the equation is very closely tied to the figure. So we have the same thing for the capacitor. Once again, the current is shown in the direction from plus to minus. The plus is at terminal A, the minus at terminal B, and we have the relationship I is C dV dt. Now what we did in class is we took this equation and we took its Laplace transform. And given that this is a derivative, we used the derivative property, and what we obtained was this equation over here on the right, where V is SL times I minus Li times 0. Now, if you look at this, this is a voltage, and this is a voltage. So when we make a replacement, actually this voltage is going to be the voltage drop across the inductor in the Laplace domain minus a drop that looks like a source. So the source would be in the different direction from the voltage labels at A and B, and it would look like this. Now, a more straightforward way to look at this is to look at the current rather than the voltage. And often when we're working with inductors, we work with currents because in the inductor, it's the initial condition on the current that determines the behavior of the circuit. So if we look at this circuit on the right, this is basically just a source transformation of the circuit on the left, where we converted the voltage source to a current source in parallel with an impedance. Now this lines up much better with our time domain circuit because we now have an inductive impedance that has the impedance value SL. The voltage drop is from terminal A to B. The current is into terminal A. And now if you look at this equation, which is simply an algebraic rearrangement of this equation, we have basically two current sources added together, which means that would be two current sources in parallel. The first current, or two currents in parallel. The first current is the node voltage V divided by the impedance SL. So this first term represents the current through the inductor. The second term is a current source that represents the initial condition on the inductor. So as a general rule, when you have an inductor with an initial current and you want to convert the circuit to the Laplace domain, the inductor becomes the inductive impedance SL. The initial condition on the current becomes a current source with the initial condition on the current and the current source being in the same direction. And so you actually have two terms then that make up the current through the inductor. The term due to the initial condition and the term due to the voltage over the inductive impedance. If the initial condition is 0, then we zero out the current source, which you probably recall from Circuits 1 means we replace it with an open circuit. In that case, the only thing that would remain would just be the inductive impedance. The capacitor is similar. We have the equation for the capacitance in both differential and integral form. If we take the Laplace transform of the integral form of that equation, we get the following, where the V sub 0 goes to V sub 0 over S. The reason that occurs is that really yes, it is a DC voltage, but it's a DC voltage that begins at t equals 0. So it's actually a DC voltage times a step function. So when we transform it, it becomes V0 over S. This integral becomes 1 over SC, because an integral, or sorry, I over SC, because an integral goes to 1 over S in the Laplace domain. The unknowns here are V and I in every case. But on the right-hand side, V and I are functions of S, so you notice they're written as capital letters. And on the left-hand side, V and I are functions of time, so they're written as small letters. So for the capacitor, when you have a capacitor that has an initial condition on the voltage and a current and voltage defined in this way, you replace that with a capacitive impedance in series with a voltage source equal to V sub 0 over S. And the direction of the polarity of the voltage source will be the same as the polarity of the voltage that forms the initial condition on the capacitor. The same is true of signs. If V sub 0 is negative 3 volts, then over here you would have minus 3 over S, and you'd leave the sign the same. If the polarity were reversed, then you would reverse the polarity here. So basically you duplicate polarity and sign in the source over here. All right, well, there's a sequence that you go through when you want to convert circuits to the Laplace domain. You don't have to do the steps all in exactly the same order. So the first thing you want to do is you want to convert all the switches to sources with step functions. So in the time domain, we often will have a DC source that's switched on or off. In the Laplace domain, you want to represent that, first of all, in the time domain as a source with a step, and then you can transform the step function to 1 over S in the Laplace domain. The second thing you want to do is you want to convert all the time domain sources to the Laplace domain. So once you've gotten rid of those switches and replace them with step functions, then you convert all the time domain sources to the Laplace domain. In Laplace analysis, the sources do not have to be DC. They actually can be any function, because basically what you're going to do is you're just going to take the Laplace transform of the time domain function of the source, and then that will represent a Laplace domain function of the source. The third thing you want to do is you want to replace all capacitors and inductors with their Laplace equivalents. And that includes, if there are initial conditions, you will need to include those sources shown in the previous figure to fully represent the capacitor and inductor. And then finally, all the unknown currents and voltages in the circuit are no longer functions of time, they're now functions of S. So you'll need to convert those to symbols that are functions of S. One thing to point out here is that you never mix time domain and Laplace domain. Just like you don't mix it mathematically, you don't mix it in the circuit. So here's an example of a simple RC circuit. We have a capacitor with an initial voltage. At t equals 0, this switch closes, and some current will flow through the resistor. And so if you, without really solving this circuit, let's look at what would be involved in transforming it to the Laplace domain. So first of all, and not shown here, the fact that this switch closes at t equals 0 means that this step function voltage on this voltage on the capacitor appears to have a step function kind of behavior. So, but there is no source. So we don't have a source that we would replace in the time domain with a source times the time function. So basically then on the capacitor, we're just going to replace it with the equivalent circuit. Let me show you that again. We're going to replace it with this equivalent circuit. So we'll have a voltage source in series with a capacitive impedance of 1 over SC. And note the polarity on the voltage source has the plus at the top and the minus at the bottom. The same as what was labeled in the figure. The value is V sub 0 over S. The switch is gone. We now have a capital I current that's a function of time, or of S, as opposed to this one, which is a function of time. And the unknown voltage across the resistor is now a capital V. That will be a function of S as well. Just to show you, you may recall, we'll go back to this table. You may recall we had two options here on replacement of a capacitor, the series or the parallel. As a general rule, in capacitors, it's typically easier to do a series circuit because the voltage is already a voltage and the series circuit has a voltage source. But there's no problem if the circuit is easier to solve in doing the source transformation conversion or the alternative replacement, which would put a current source in series with that capacitive impedance. Otherwise, everything remains the same. Here's another example. In this example, you have a DC current source and some various elements. The unknown current through the inductor is what we would want to solve for. In this particular problem, the switch was closed for a long time and then it was opened at t equals 0. So sometimes you'll be given initial conditions explicitly, other times you'll be able to solve for them. In this particular case, you can solve for the initial conditions knowing that before the switch moved at t less than 0, all of the current was going through this short, which means any voltage that would have been on the capacitor has been drained away. Any current that would have been going through the inductor has been drained away through the source. So all of the initial conditions on C and L will be 0 because of the fact that this circuit was short-circuited. So we start out with 0 initial conditions, which means we will not have an initial condition source with the capacitor or the inductor when we convert them to impedances. This current, because it will switch on at t equals 0, could actually be represented as 24 milliamps times U of t. So when the conversion is done, that's going to be taken into consideration. So here's what that circuit looks like. Notice here's that DC current source, now divided by S to represent the fact that it was switched on at t equals 0. The capacitor has been transformed into a capacitive impedance. The inductor has been transformed into an inductive impedance. The unknown voltage and currents across the inductor have been transformed into functions of S because they are capitalized. And notice that there are no sources present in series or parallel with the capacitive and inductive impedances because those initial conditions were 0. Here's another example. In this example, we have two meshes. The switch was open, meaning no current could flow through this 8.4 Henry inductor. This was a closed loop, which means that any current that was present in the 10 Henry inductor before 0 has had more than enough time to drain away on the connected resistors. So we start out this problem with 0 initial conditions. The 336 voltage source is switched on at t equals 0. So the result is that that voltage source becomes 336 over S. The inductive impedance becomes SL, or 8.4S, and 10S here. The resistances transfer over exactly the same, and the currents now become functions of S. So it would be possible, we're not going to do it here yet, but it would be possible to write some mesh equations for these two meshes. And then the only difference is that when you solve for I1 and I2, they're functions of S, not numbers. So that would be the difference between a Laplace type circuit and a DC circuit. And here's one more, just to show some additional examples. This is also a case where the switch was open for a very long time. So obviously there was no energy stored in this part of the circuit. And then at t equals 0, this switch closes. And in this example, the textbook is looking at the fact that you can use a Thevenin equivalent in the S domain. So we're not going to actually reteach Thevenin equivalent this semester because we kind of assume you know it. And there are other things that we want to cover in the course. But I will walk you through what they've done in this example. So before doing anything else, the entire circuit was converted to the Laplace domain. So because of that switch, the voltage source becomes 480 over S. The resistors go as resistors. The inductor becomes SL, and the capacitor becomes 1 over SC. So here is the function in the Laplace domain. What we want is we want the current and the voltage for the capacitor. So in this example, your textbook author is going to do on the left-hand side of the circuit shaded in blue, He's going to do a Thevenin equivalent. He's going to do that by determining the open circuit voltage and the equivalent impedance when looking into the source direction. So I will talk you through that verbally. Basically, to find the open circuit voltage, you want the voltage across this impedance, and that can be done by creating a voltage divider. So you take the voltage source, 480 over S, times this impedance, 0.002S, over the sum of this impedance and 20 ohms. That would give you the Thevenin equivalent source. The Thevenin equivalent impedance, we will look into the terminals from the right-hand side toward the left-hand side. The voltage source is killed, so it will be shorted. That'll put the 20 ohm and the 0.002S in parallel. So you find the parallel combination of those two and then add it in series with the 60 ohm, and that's your Thevenin equivalent impedance. So here's the result, and you're welcome to practice this if you think you need more practice with Thevenin. But here's the results. Here's the source after it's been calculated at the open circuit terminals. Here's the equivalent impedance looking into the Thevenin part of the circuit with the source killed. And then here's your load. So now calculating the voltage is a simple voltage divider, which is actually not so simple because you can see we have all this algebra here. And calculating the current is a matter of taking the voltage and dividing by the entire impedance in the circuit. So those are just some examples. What I want you to get out of this today is not how to solve or not how to find a Thevenin equivalent, but more the steps involved in taking a circuit from the time domain to the frequency domain. So that concludes what I want to go over in this part of the lecture.